Okay. What thermodynamic function focuses only on the system to predict spontaneity that allows us to get over that limitation with the second law of thermodynamics? And this function is Gibbs free energy, or simply free energy. Free energy change in free energy. They all mean the same thing. This allows us to predict spontaneity of the system alone, and it's equal to, or its equation is the change in free energy is equal to the change in enthalpy minus the temperature times the change in entropy of the system. So if delta G is less than 0, the reaction is spontaneous in the forward direction. If it's greater than 0, the reaction is non-spontaneous in the forward direction. So you may already see that it's opposite of what we see with change in entropy, right? Which is positive for spontaneity or for spontaneous processes. Delta G is also equal to 0 when the system is at equilibrium. So looking at this equation for the change in free energy and understanding the relationship or the impact that enthalpy or an entropy will have on free energy is an important thing to look at because it can give us insight into when a system will be spontaneous based on the change in free energy. And I should say, though we can look at enthalpy and entropy in predicting spontaneity, delta G gives more of a complete picture, right? And that's really what this chart here is showing, right? It's really summarizing all of this that we've talked about: enthalpy, entropy, and now free energy as it pertains to spontaneity. So we know delta G is less than 0 for a spontaneous process. So if we look at when delta H is greater than 0 for an endothermic reaction and when delta S is less than 0, greater than 0, what will be the value of delta G? So this is like a mathematical question, right? You could plug in different values and play around to see this. But what you'll see is that if this term here is positive and this term here is also positive, really the sign of delta G is determined by temperature. It's determined by temperature. So when delta G at high temperature, we see that delta G is less than 0. And at lower temperature, delta G is greater than 0. So under these two conditions for enthalpy and entropy, the process or the system is spontaneous only at high temperatures. Only at high temperatures. Now, if we have a system where delta S is less than 0, so this term here is negative, right? And this negative times this negative will cancel out and be positive. We see that it doesn't matter what the temperature is, delta G will always be greater than 0. It will always be positive at any temperature. So under these two conditions, delta H being greater than 0 and delta S less than 0, the process will always be non-spontaneous at any temperature, right? So we do the same thing looking at an exothermic reaction based on an enthalpy, change in enthalpy that is less than 0, and we see that delta G is less than 0 at any temperature. So the process is spontaneous at all temperatures. when delta S is greater than 0. But when delta S is less than 0 and delta H is less than 0 also, delta G will only be negative at low temperature and positive at high temperature. So the process is spontaneous only at low temperature under these conditions. Look at this chart. Plug in values. Learn it. Make sure that it sticks and make sure that mathematically you're able to make sense of why we see what we see here in this chart. All right. So let's say that a problem asks you to calculate the temperature at which the spontaneity of a reaction changes, right? Whether when it goes from spontaneous to non-spontaneous or non-spontaneous to spontaneous. And in this case, we are given the change in enthalpy and the change in entropy. So we would find the temperature at which delta G is equal to 0, because we know at 0, it's at equilibrium. So if we find that temperature at equilibrium, then we're able to glean and see what temperature would the direction of spontaneity change. And there's some example problems of this in the discussion worksheet for this week. All right. So standard free energy, just like with enthalpy, we can calculate standard enthalpy changes, we can calculate standard entropy changes, we can calculate standard free energy changes. And it's valid under standard conditions. Here is our equation. So there's really two ways that we can calculate standard free energy. One is using the equation that takes into account enthalpy change as well as entropy change. I made a note here to make sure, right, your units match up, because in changing free energy is given in kilojoules, right? Whereas with entropy, it was given in joules. So you'll, depending on which way we calculate it, you will want to make sure that your units are matching up. All right. So as I mentioned, right, again, these are the standard conditions. When a process happens under standard conditions, we can calculate the standard free energy change by using experimentally determined standard free energy change of formation. So this is an example. For this reaction, it was experimentally determined that the standard free energy of formation is negative 237.2 kilojoules per mole. Now, another way that we can calculate standard free energy change is similarly to how we do standard change in enthalpy as well as entropy. So this is like a general schematic or general chemical reaction, right? A and B are our reactants, C and D are the products, M, N, X, and Y are our coefficients. So for this reaction, the formula for how we would calculate the standard free energy change would be as follows. We would sum over the standard free energy of formations that were experimentally determined for our products, right? Multiplied by the coefficients for each product, sum those together minus the standard free energy change of formation of our reactants times their respective coefficients. Same way for standard change in entropy as well as enthalpy. So, same formula. Summation over standard free energy change of formation of products minus that of reactants. So if we're calculating free energy change under non-standard conditions, this is the formula that we would use. We're going to come back to this later when we talk about equilibrium, but I just want to mention this now. So T is our temperature, R is our gas constant, and Q is the reaction quotient. And if reaction quotient is foreign, or maybe you need to review it, look it up and remind yourself how we get the reaction quotient. Okay. So just like with enthalpy, right, free energy changes for reactions are additive. What I mean is if there is a process that can be broken down into stepwise processes, which we talked about last week with enthalpy, then if this is also true when looking at free energy, reaction 3 is equal to reaction 1 plus reaction 2. This is what we mean by saying the reactions are additive, meaning there's two steps, reaction 1, reaction 2, that will give us reaction 3. If that is true, then the change in free energy of reaction 3 is equal to the sum of the change in free energy of reactions 1 and 2. An important thing to note is that if the reaction is reversed, then the sign on delta G is also reversed. And if the reaction is multiplied by a factor of n when we're adding these two reactions, we'd also multiply the change in free energy by that same factor. We will have problems like this in the discussion worksheet. So I want to conclude this section, right, with the question that we started with. How are geysers and an everyday activity like boiling water a display of thermodynamic principles, right? We talked about spontaneity, we talked about entropy, we've talked about change in free energy. And the first thing that comes to mind, right, or that may come to mind for you is thinking about how phase changes, right? How phase changes are a factor that influence entropy. So just within a geyser, heating up that water under the earth results in the water, basically it increases the microstates of the water, right? And so it explodes out of the earth as liquid as well as steam. Increase in number of microstates, right, becomes a spontaneous process, right, as well as an increase in entropy, right, which is why we have these geysers forming. Similarly with boiling water, right? Once we reach the boiling point of water, we go from liquid to gas, right? And we saw that in that graph where we saw phase changes, going from a liquid to gas increases the number of microstates that the water can be in, therefore increasing entropy as well, right? Spontaneity. These are examples of spontaneous processes. Examples of spontaneous processes. So this concludes our discussion on thermodynamics for now.